a little bit on isomerization chemistry. Remember that isomerization is nothing more than trying to rearrange the structure of a compound or a molecular formula. And what we're going to keep is the total number of carbons and hydrogens, and of course if there are other atoms, we're going to keep the total number. We're going to keep the total number of single bonds, double bonds, and triple bonds if given. And what we're going to do is essentially just try to modify the structure overall. Now remember that, for instance, pentane has 5 carbons and a total of 3, 5 times 2, 10 plus 2, 12 hydrogens. As you can see here, isopentane, please count them out, 5 carbons, and if you were to count all the hydrogens, you will count 12 hydrogen. So you can see here, this is linear, this is branched. Now remember that typically branched hydrocarbons will increase the octane rating because they tend to not combust easily, and the linear ones will interact easier with oxygen. So that's a very rough estimation, but typically iso structures are much more high on octane rating than N structures. So here we go. Primary reaction is to convert normal paraffins. Remember, normal stands for linear. This is N-pentane actually. When we say pentane, actually we cannot know which one it is. We need to state either N-pentane, isopentane, or sec-pentane, and so on. 2 isomeric paraffins. Isomeric, as the name implies, has a iso branch. Olefins may isomerize and shift the position of the double bond, so that's interesting. So we have here 1 butane. 1 butane is something like this: 1 carbon, 2 carbons, 3 carbons, 4 carbons. 1 butane has the double bond here. What we try to do is to convert this to either this one right here or this one right here. And then, of course, we try to hydrogenate this in order to convert this to a useful material. Cycloparaffins, technically naphthens. Remember, naphthens are cycloparaffins. This example is this 3 carbon molecule, 4 carbon molecule, 5 carbon, and you already know these ones. These ones are common: cyclopentane and cyclohexane. In this example, cyclobutane, this one right here, will be broken into cyclobutane, which is this one right here, which later on can be converted to these ones here, and then converted to more stables, and then convert to isobutane. So here's an example. N-pentane can be converted to 2-methylbutane. Why butane? You have the long chain, which is butane, for carbon chain, and in the second carbon you have this other carbon, methyl branch. Or 2,2-dimethylpropane. Propane stands for the longest chain, which is 3 carbon, and in number 2 we have methyl branch 1, second methyl branch. So that's why 2,2-dimethylpropane. Now let's get a little bit more into the catalyst side, which is what you're going to cover mostly here in the overall conversion of refinery. In the refinery, you're going to have zeolites, which is something like this, cubical structures which favor sites of reaction, and chlorinated alumina. And you can see here, the idea is to have micropores, so it's easy way going in and easy way going out, but in this specific case you're going to have a higher interaction or more area to interact with the reaction. Remember that catalysts, what we're going to do is favor the rate of reaction. Zeolite catalyst requires higher temperatures, so that's a disadvantage, and provide lower octane boost, so that's bad. So probably you're wondering why will we want to use zeolites. We're going to see it later, essentially because these zeolites are heavier, or it's a little bit more complicated to poison it compared to chlorinated alumina. On the other hand, chlorinated alumina will have a higher octane rating, doesn't need to operate at high temperature, higher sensitivity, but because of the same higher sensitivity, we're going to require to remove or pretreat most of the feeds. So we need to remove oxygen, water, sulfur, nitrogen, and other metal containing compounds. Zeolites, on the other hand, are crystallized silicoaluminates that are used to give an acidic function as a catalyst. Remember before we have seen a lot of hydrogen sulfide or sulfuric acid, phosphoric acid interaction, even hydrofluoric acid, those are providing a proton, which is the acidic catalyst. Metallic particles of platinum are impregnated on the surface of zeolites. These particles act as hydrogen transfer centers. Remember these hydrogens. The zeolite catalyst can resist impurities, so that's an advantage compared to the chlorinated catalyst. Does not require extensive feed pretreatment, which is awesome, and that means that our catalyst is going to last longer. But as stated before, has lower activity, will require high temperatures, and it's one for the other. Now let's continue to the process description of isomerization.